I am in the doubts how to proceed. I can mumble for a long time about the principles of what is software and how it works. Or I can go directly to a practical thing, and then we will pick up the rest as we go. And also, if anyone is interested to have a meeting during the break, just not as a scheduled thing, but just to like questions and answers, send me an email, and I will be more than willing, because I'm not traveling anywhere and can and probably you do not have other classes, so we can meet a couple of times if needed. Okay, so the new software that we are starting, the name is VASP, Vienna Ab Initio Simulation Package, and it can do, there is an area of expertise where this piece of software overlaps with Gaussian. There are areas which are available only for Gaussian, not to us, but there are a lot of areas where VASP is unique and can do good things for us. So the main skills that, well, I will probably chop or add another things, but basically those are subjects for the presentations that we will do in about 3-4 weeks from now. So as we go through these materials, we will practice the same arrangement as we did two other times. And I will start covering them as much as possible. But basically, the minimalistic goal of today's meeting is to get this image, which corresponds to the density of states of the same molecules that we did on the lab number 5 before. I think Dr. Han was covering it, right? So titanium hydroxide, 1 titanium, 4 OH groups, and there are occupied, there are unoccupied, there is a band gap. And since calculation here will be done not with Hartree-Fock, but with DFT, it will be more close to the reality, where the realistic band gap is about 3.5, and here is not far from it. So this software, I'm paving a way that doesn't bring any surprises. It will first go through the things that are very similar to what we did with Gaussian. So the density functional theory, same as Hartree-Fock, uses concepts of orbitals. There are occupied, unoccupied. There are like iterative protocols. And as soon as we get total energy, we get energies of orbitals, we can represent them in the form of density of states. This is not the whole story, but it is something practical that we can get in a limited time. So there are several other things that I need to give as a disclaimer before we go forward to practical aspects. Today's meeting, which is introductory, we will run VASP software on a photon cluster. And to those who are only interested in like a little background education and a grade, it is enough. But if you are seriously considering using the software for projects, we will need to run the software on the high performance facility. And after we will, I hope we will be done with reproducing this figure in maybe an hour, just learning the software and basic things. And then as time allows, I will try to give an overview how to log into cluster and how to submit jobs, and at least to reproduce the same thing on the remote cluster, on the not photon but true cluster. Okay, and this part that we will be doing close to finishing of today's meeting will be most challenging. Just by observing how it went in previous years, because as soon as we run jobs on a remote cluster, we will experience a challenge of file transferring in a command line. So this is nothing difficult in principle, but it is so boring and exhausting that many people give up and tell, okay, I will not do it. I will just do little exercises on Photon and avoid file transfer. So if you really have some projects in mind, if you want to use the software productively, just concentrate, prepare your internal strengths for going over the barrier and running on the remote facility and sending files forward and backwards, which will be, it's not a big deal, but it is uncomfortable. Just prepare. Okay, so I will briefly show some slides, and they're not smart and useful, but I do not have anything better. They were serving each year quite efficiently. Okay. So the Gaussian software that you all are certified experts in from now on, right, uses a single input file, right? .com that includes, according to our speakers on Monday and Tuesday, it includes parameters, the way to interact with cluster if it is on the remote facility, like memory, number of processors, then the special line for type of job that we need to do, method basis set, which we can click in the Gauss view, or we need to type in the input file. And then there are numbers for charge and multiplicity, and then there are atomic coordinates, right? So everything we want from this software, from the computation, is encoded in one file, which appeals to human brain quite naturally, right? So in the next 15 seconds, I will tell you why a lot of bright researchers decline to use WASP. Instead of one input file, it uses 4 input files. And so the things that Gaussian encodes in one file, and all service commands are condensed in like maybe less than 10 lines at the top. In WASP, there are 4 different files. So there is one file that contains positions of ions, and it is called Postcar. I have no idea what is car, although I am running the software for last like 15, 17 years. But post stands for position. So the request for like doing either SCF or energy optimization or frequencies or whatever is hidden in the file that is called incar. Then there are 2 other files. We didn't have presentation on basis sets, but Adam briefly covered it, right? And when I just photographically remember your presentation, if you scroll through the drop-down menu for basis sets, at the bottom there was an abbreviation ECP. You remember? I know that Lola and Haley are doing practical research computation with Gaussian, and I would like to ask them what is ECP if you saw it in your research life. Lola, would you like to speak up? We don't hear you. We need to change the just a second. I think you are speaking, but we do not hear you. I need to update the speaker.
How about now?
Number one, please try.
I'm speaking. Can you hear me?
Speaker number two, please try.
How about now?
Doesn't work. Speaker number three, please try.
Can you hear me now?
No.
Oh,
Speaker number four, please try.
do you hear me now?
Oh, yes. Excellent.
Okay.
Okay, yeah. So what is ECP?
Effective core potential.
Effective core potential. Haley, do you approve? Okay, yeah, Haley approves. So what is effective core potential? Just briefly tell what it is and how it relates to the basis set.
I'm not exactly sure, but I can try.
Yeah, just try.
So instead of using the valence electrons, it uses the core, the electrons that are inside the shell, not on the outer shell. I don't know if that's right.
Okay, so some electrons are treated explicitly, and some core electrons are skipped from explicit consideration, but we have their influence on the mean field potential, right?
Yeah.
Approve? Adam, would you approve this statement? At least you do not oppose. So in heavy atoms, there are outer shell electrons that really affect formation of molecules, and there are deep electrons that affect only like X-ray spectroscopy, but do not participate through chemistry, right? But these electrons that are on the very low atomic levels still contribute to the potential that last electron in Hartree-Fock theory experiences from the average potential. So effective core potential. Effective because we do some cheesy tricks. Core because they're core electrons, and potential because it is electrostatic potential. So in Gaussian, the effective core potential keywords, and we were successful in this class without mentioning them because they needed only for heavy elements. In VASP, one needs an analog of these specific potentials for each ion. So it gives specifics of the elements that are used in that compose certain molecule. And the information about this share screen, share. And information about this elements involved in the molecule are saved in the Podcar potentials. So, and there is a file number 4, which is listed as S3 K points. We will use a template and do not touch it until our meeting in 3 weeks from now. But here, the file K points is a mysterious thing that makes a dramatic difference of VASP code from many other codes. So it was created to describe not only chemistry, but also physics and engineering. So the VASP code is intentionally created to describe solid periodic materials. And if you have like metal or semiconductor, there are circumstances when electrons in this model do not stay still in their orbitals, but they are collectively moving through like a wave on a lake. So if you have a big piece of metal, there are electronic waves that are continuously moving with constant velocity. Make sense? And this K points file adds details on about this constant motion, because there could be superposition, like one wave goes to the left with constant velocity, another to the right, another wave stands in the center. When we use VASP for isolated molecules or quantum dots or like donor bridge acceptor complexes. We do not need the specifics. But as soon as we add periodicity, this will be a key factor to include. And to be generic, one needs to have this file all the time. So the minimalistic goal for today is to create this 4 files for our titanium hydroxide, run, get output, and generate density of states. Make sense? Okay. I'll still show a couple of this ugly handwritten slides just so that we are on the same page and approximately have general idea what is going on. I'll show only things that is hard to show practically. When we were living in the world of Gaussian, we were not worrying about environment, or Gaussian allows us to worry about environment in a sense of solvent or polarized continuum media, when a molecule is surrounded by dielectric of this or that dielectric constant. And this polarization of, we didn't cover it in the class, but it is easily recoverable just by pushing buttons in the Gaussian submission window. So one can modify a calculation, but assuming that our molecule is immersed in the dielectric, which reproduces, which mimics a solvent. And then due to polarization of solvent, the energies of all orbitals and total energy change. But in Gaussian, we were not thinking about how far the solvent goes. We were assuming it is infinite. And when we were doing cubes for orbitals, we thought just some reasonable space around molecule, but we were not thinking about any boundaries. The paradigm, the mindset when of the VASP software is different in this aspect. So one believes is not the right word. One accepts a paradigm that the whole world is made of cages or boxes. World, not in a sense like we are in like cages, but if you look on a periodic structure, right? On a crystal, we see that there is a repeating pattern, right? Or if you look on the conjugated polymer, right? On the polymer, there is a repeating pattern that repeats again and again. And in order to think about crystal or polymer, one do not need to have infinite cell to include everything. One can look only on small cage, which includes this periodic pattern. And then we believe that the nearby cages have the same atoms, the same internal structure, right? So we need to accept this paradigm of world consisting of cages or unit cells or simulation cells. If we want to use VASP for the same purposes as Gaussian, if you just decline its major strengths and apply it back to the chemistry, then we need to just make a big enough cage where our molecule is surrounded by vacuum, right? But we need to be specific how much vacuum we need to include around our molecule. And this ugly hand drawing represents this. So we have a molecule in the center, and then we need to say that we have an offset of vacuum to the left and to the right. So we will practically add this vacuum offset. And it may sound ridiculous, it may sound unnatural, but we will need to do it again and again each time we prepare input for VASP calculation. If it is a real periodic cell, if you borrow the structure from database, or from a colleague, someone can do it for us. But if we prepare a model ourselves, we need to explicitly mention this offset. Okay. I know that your patience is not infinite, and I will stop this story soon and we'll go to practical things. Another aspect, in the whole class, we are going to work only with rectangular cells. But in principle, there are some crystals where cells are not rectangular, tilted, like hexagonal or whatever. And at the beginning of the Postcard file, which includes positions of ions, there is an information about size of this cage. Since we are working with rectangular cages, this information is stored in the matrix 3 by 3, where only diagonal elements are non-zero. And then it will correspond to size of the cage along X, Y, and Z. If it would be tilted, then there will be off-diagonal elements. We just want to live an easy life and skip it for now. Okay, so the Postcard file includes size of the cage. And there is another aspect of discomfort. I'm just giving you a heads up, but we will go over the things again and again. I'm just giving a little heads up. When we were playing with Gaussian or any other software like Avogadro, what else did you try? JMO, maybe something else. We were always giving positions of ions in absolute units, typically in angstroms, right? So this hydrogen atom is offset from the origin by 10 angstrom on X, 1 angstrom on Y, and 3 angstrom on Z. If you look inside, and we will look inside typical WASP files, you will see that there are 3 coordinates, but they all take values between 0 and 1. They even if you have a large system, the values of coordinates take value between 0 and 1. And here is what it is. So it is fractional coordinates. Actual coordinate divided by size of the cell. Actual coordinate y divided by size of the cell in y. And this and z divided by size in z. So this approach allows this piece of code to be universal and to treat simulation cells of any size in the standardized way. So it just in the world of WASP, all coordinates are fractional coordinates and they take value between 0 and 1. In order to recover actual coordinates in our realistic space, we need to multiply them by size of the cell in each direction. Okay. Yeah, I think enough. If needed, I will return to this presentation. So let's go through practical sites to get to this figure. So let me invite everyone to use MobExtern, log into Photon, and maybe create a directory for today's lab. So I will create another subdirectory so that I do everything in U. And so I am starting with the titanium hydroxide Gaussian output file, because we played with it a lot. I did borrow it from myself, from my directory. If any of you did optimization, better start with optimized geometry. So I do have Gaussian file. Now I want to convert it into XYZ. So I'm using Babel. I don't remember all commands, and I just Babel minus H capital gives a list of formats, and there is a Gaussian 09 output. So it is what we have. So Gaussian Babel minus IG09. Then I have only one file in this directory, and then minus I minus out O for output XYZ. I can call it same way, but dot XYZ. So I'm looking more XYZ. It has Cartesian coordinates of the molecule that I want to deal with. So let me copy paste this command into the chat line. I have no doubt that everyone is aware of it, but just in case. Okay. Another thing. The Gaussian is closer to human mindset. It doesn't matter in which order we draw and list atoms. So we have their labels like oxygen or hydrogen, oxygen or hydrogen. It's enough to identify an atom and put it, give a right potential to right atom. So we see there is a like alternating order, OH, OH. If you do the same, you made me. Okay, thank you. Okay. Whoa, and you can make localhost just in case. Or... Oh, hello, Hanmant. Nice.
Hello.
I think we are a little too loud. Let me reduce the volume. Okay, so you see it is sorted, and now we can do forward this into the new file. Let's call it postcar.xyz. So right now, let me copy paste this into the chat line as well. Copy, chat, paste, enter. So if I look inside this file, so it has the same thing. So I want to manually edit it, vi postcard.xyz. So first, in the XYZ format, first line should tell the number of ions. And then there should be names and Cartesian projections. So for hydrogens, for oxygens, and one titanium. And then I do not need anything else. Escape, column WQ. So manually edited the Postcard file so that it will be organized, like apples to apples, hydrogens to hydrogens, oxygens to oxygens. Make sense? Please try to do the same as I'm doing. If needed, I will make a tour and make sure that everyone is on the same page, but it's better if I just go forward. So just attract my attention, raise hand if something doesn't work or you want me to be slower. I will. Okay.
This is just a quick question. Like I copied the titanium oxide that we did for the last lab, and so it's more ions than this one. Is that okay?
So right now, for educational purposes, it doesn't matter which molecule we are doing. But if we want to be scientifically and chemically reasonable, then it's better to start with 1 titanium and 4 OH groups because it is a closed shell. If you go to this complex with 6 waters, then we need to do open shell, which is available in VASP, but it will be too much to start with. If it's too many challenges, do whatever you can. And also you can borrow the geometry from me or from each other. So just copy it from my directory if needed. But closed shell titanium hydroxide is better, but it's not nothing to panic about if you started with other molecule. We're just going through the practical protocol, how to do things. Haley, you raised hand. Yeah, answered. Amir? Oh, fine. Adam? No questions? Oh, okay. One molecule. Sorry, we shouldn't worry. Just look inside the file. If the file is reasonable, just do not worry. So if your Gaussian file was originating from optimization, then you will have XYZ file with, it may include several replicas. And then we need only the last one. If it was an SCF job, it will be only one replica and everything is fine.
Okay, I see.
Okay. And let me copy paste the directory. So if something doesn't work, right now we are not doing things for grade or for test. So if something doesn't work, feel free to borrow from my directory. It's better if you use your own data, but just do not panic if your data do not give things. Okay. So right now I do have this postcard file. It is not in the VASP format. It still has this absolute values, which can be negative 2.2. So it's a real molecule. A conversion from XYZ to VASP is a 2-step process in the protocol that I'm going to offer. There are different pieces of commercial software that do it differently. So if you see other way that I'm going to show right now, feel free to use it. Feel free to report it on the presentations or use to your project. But I'm going to show something that will be reliable, even if you do not have graphical connection, and something that works in a command line in a reliable fashion. So no, just a second. So I am going to launch a command that is I'm just waiting until this panel disappears. Oh, maybe I can pull it. Oh, yeah, it's better. Rotate XYZ. So this doesn't have scientific meaning. It is just a script that rotates molecule in 3 dimensions if you need to do like docking or attach. But at the same time, it changes format. Rotate XYZ. And then I answer 0 3 times. So I'm not going to rotate. Rotation along X, Y, and Z axis is 0. After launching this command, I am obtaining new file, which has a longer name, postcard_write rotated in the Tinker format. I don't care what is inside, but I can just for curiosity look. So it will be slightly different format for Tinker software, which I do not use, but some of you who do force field molecular mechanics may eventually use. Amir, do you? Venjan, do you use Tinker? Okay, so then if anyone wonders what is Tinker, ask Venjan. Now, after I do have this file, I'm going to the second stage, and I'm typing tink to wasp, name of this file, Postcar rotate XYZ, Postcar, which will be output file, and then I give 3 parameters. Well, if you're superstitious, maybe 666 is not good. Let's do 777 or 555. So those 3 numbers are amount of vacuum in each Cartesian projection that we add to the molecule. So the molecule itself has a size of about 3 angstrom. If we add about 5 angstrom in each direction, the cell will be about 8 by 8 by 8. So let me, before I run it, let me copy paste this template into the chat line. So after it is done, I am looking for new files. By the way, before to look through the new files, it gives this length 0, 1, and 2. It gives the size of a molecule that it would take if we do not add the vacuum. So it's size of the molecules if we stick them one to another, shoulder to shoulder. So it's like about 4 in X and Y and about 3 in Z. And it is about 9 after we add this adjustment. So I am looking for new files. So you see at 542, there was new file named Postcar. This is a Postcar input file for positions in the WASP format. So more Postcar. So now it is the thing that I was giving a little warning to and heads up to everyone. So it has names of the elements the molecule is composed of in one line. So instead of giving name of the element in front of each line with coordinates, it tells that just molecule is composed of hydrogens, oxygens, and titaniums, right? And 1, 2, 3, 4 lines later, it tells here's the stoichiometry: 4 hydrogens, 4 oxygens, 1 titanium, right? And then the list of Cartesian coordinates should be interpreted in the following way. So hydrogens, there are total 4 of them. So first 4 lines refer to hydrogens. So the next element is oxygen. Total number of oxygens is 4. So second 4 records are for oxygen. And the titanium is coming only once. And it is just 1 record at the bottom of the file. Okay. So second line is a scaling factor. If we need to consistently shrink or expand the whole lattice, we just change this number. If we do not do it, we just keep it as is. And here are the size and geometry of the simulation cell. So if it is rectangular, it has only diagonal elements, and it is about 9 angstrom in X, Y, and Z, right? So the molecule is typically placed in the center, so about 0.5. And this fractional coordinates, if we multiply X fractional coordinate on 9, we will get the values projection in angstroms. And same for Y and for Z. This letter TTT means translate or thermalize. If we do not want some ion or some degree of freedom to be optimized or moved in molecular mechanics, molecular dynamics, we can replace it to F, like frozen. So we can freeze everything or part of a molecule or allow it to move only in certain direction. So it gives a lot of versatility. So to explore partial motion. Okay, so Postcard file is done. Please show this file on your screens. I quickly run over and make sure everyone has it. No. Okay, yeah. Let me just. So there should be space between number of ions. Second line should be empty, or you can just tell it's nice weather today or whatever. I am doing computational chemistry.
Okay.
Okay, so rotate XYZ. So there is a Postcard rod and it is non-zero, right? Now we do square root, then input, output, and adjustment parameters. Okay.
Thank you.
My pleasure.
I have this.
Okay, let me check it.
I came up with the part that we have this postcard, but I did not. Yes.
So space between number of ions and coordinates. Oh, whoa. Did I screw up something? Oh, no, not yet.
Yeah.
Let's probably put it. It took me 3 years to learn this software. I was resisting to my advisor, telling I hate it. No. It's just convention. It's empty line between.
Thank you.
Thank you.
Yep. So empty line. So once again, so empty line between 9 and coordinates. Okay. Oh, thank you. I for insert, enter for empty line. I for insert, enter for empty line. Escape, DD for erasing. WQ, more, Postcard XYZ. So it's empty line between 9 and coordinates now. Rotate. Okay. Oh, thank you, thank you. Good, excellent. Rotate XYZ. 0, enter, 0, enter, 0, enter. Sync to us. Scar underscore Scar.
I don't know why.
Okay, that's okay. Where should I type? Let me type here, and then in here. More postcard dot xyz vi postcard dot xyz. I enter. Escape. D escape. Column WQ. Rotate underscore xyz. 0 enter 0 enter 0 enter. Sync to wasp. Postcard underscore rotate. Postcard. More. Postcard.
Thank you. Thank you.
Yeah,
Yeah, I can follow.
okay.
I'm not sure why there's this runtime error, but I was able to create.
Okay, yep. Yep. More postcard dot xyz. Vi postcard dot xyz. Second line, I enter. There should be empty line. Or one can type comments. Okay. Zero enter, zero enter.
So just like find between the.
Exactly. Yes. Okay, let me check if anyone is online who is Hanmant, would you please share your screen?
Dr. Killen, I missed the introduction, so I don't know what exactly I have to do.
Just share screen and I will type things. We will do it together. So I stopped sharing. Let me check if you are, yeah, you're co-host. So just share screen when you're ready.
Yes, I just.
Okay. Yep, that's great. Request remote.
So I just entered to your folder.
Okay. You need to go to your directory. Okay, let's copy. I think in the lab 6. you should have some .log files. Too many. Let's take remove everything, right? Let's take the one from lab 5. Okay. So we do have this titanium one.log, right? So quickly repeat Babel input Gaussian 09, output XYZ, XYZ. Please stop me if anything is unclear. Wow, why it takes so long? Okay, more XYZ. So we have the geometry now. Sort this titanium XYZ into postcard.xyz, XYZ, more postcard.xyz. So it's a good, the file does not, see in the previous version, standard has some comments in the second line. Now we do not have the second line, 9 and then immediately coordinates. We need to fix it. So vi postcard XYZ, you need to put empty line. And this thing is not needed, we can delete. Escape WQ. Now rotate XYZ 0, 0, 0. ls minus of t, we have new file postcard underscore rotate. Now sync to wasp. Input file is postcard rotated. Out is postcard. Adjustment of vacuum is some number, and now more postcard. You have basically what everyone else has. Make sense?
Yeah.
Okay, you may stop sharing. Sarah, would you like to share screen?
Yes, here it is.
Just go to the last one. Yes.
Mhm.
Yeah, excellent. Thank you. You can stop sharing. Lola, are you on the connection? I think by some reason Lola has disconnected. Okay, and everyone else is in the class, right? Okay, then I start sharing screen again, and so we do need 4 files: postcar, incar, kpoints, podcar. We did the most complicated. No, well, another little challenge is podcar, and incar and kpoints can be taken as a templates. So ls tilde pod pb. So there is a directory. Let me copy for your information into the chat line. So in this directory, there are potentials for all elements. And you see there, let's see, there is H for hydrogen. There are some crazy hydrogen that has more than 1 or less than 1 electron. There should be like helium and the whole periodic table plus some additional things. So we, for example, let's look on hydrogen. So, and inside this directory, there is only one file, podcar, which we do not want to look inside. It's quite big file with numerical data showing the potentials. but we do need to. Cat is not a animal with whiskers. It's abbreviation from I can't pronounce it. Concatenate, to merge together. So we need Podcar, bigger, or caret, Podcar. Now our second element is oxygen, and our third element is titanium. So how, let me copy paste this codes, because a lot of bright young researchers were declining to use WASP after failing to practice this command. I'll go a circle and make sure everyone is here. So how do I check if I didn't make an error? So first, and how do I know in which order I do them? So head, no, not here. Head, Postcar. So our positions. So I see that we have hydrogen, oxygen, titanium. Therefore, we create potentials in our local Podcar file in the same order: hydrogen, oxygen, titanium. And how do I learn that I haven't made a mistake? Because what if by human error I hit the same button twice? So grep PAW Podcar. So it shows only headers. The file Podcar is quite big, but it shows headers. So we have hydrogen, oxygen, titanium. If I would make a typical mistake is to swap the order or use more elements that, more or less elements that are in the molecule. Just make sure that those three things are consistent. The list of elements here, list of elements that you pull forward into the Podcar file, and the outcome of this little experiment. Let me make a quick tour. So it's quite simple thing, but it's a high chance of human error. Just try to make this little test, and so that I see it on your screens. HO titanium, excellent, thank you. Grep PAW Podcar. PAW projected, no uppercase, projected augmented wave. Space,
Okay.
Podcar. Enter. HOT, excellent. Everything is good. HOT, thank you. HOT. HOT. Grep. Up. Okay, yeah. So you have Podcar. Grep PW Podcar. HOT, everything is correct. Thank you. HOT, excellent.
Some error in the last step.
That's okay. That's okay. Let me be clear. So you are doing different model, right? It's something different. You have twice as bigger molecule, or you are doing this water complex. You're probably doing water complex with.
Maybe I choose this.
Okay, it's not wrong, but let's check. So we have empty space here, one titanium, all hydrogens. Yeah, okay. WQ. Now rotate. 0, enter, 0, enter, 0, enter. Everything works. Sync to WASP. Postcar. Date. Postcar. More. Postcar. Hydrogen, oxygen, titanium. 1161. Oh, okay. Good. You can keep going further. And now we need to create Podcar. You, oh, you didn't. Okay. Cat. Pod PV. H. Podcar. Caret. Podcar. Enter. H. O. T. Grep. W. H. O. T. Always good. Yeah, my pleasure. Excellent, thank you. Okay, and let me stop sharing and ask Hanuman, would you please share screen? HOT, excellent, thank you. You can stop sharing. Sarah, would you please share screen?
Yes, sure.
HOT, excellent, thank you. You can stop sharing. Okay, sharing screen. So we do have 2 out of 4 files. We have Postcar and Podcar. We need just 2 in-car and key points. Copy tilde bin in. Let's start from key points space period. So I just copy it from the template. Copy, and let me bring it to the chat line. Paste. Okay. So just for curiosity, more, no, not here. More, no, what is going on? Click. More key points. So it's quite short file. Who was traveling to Sanibel? Haley, Adam, and Will is disconnected. Did you saw 80 years old white beard in the orange shirt who was actively asking questions on the last day? Oh, you didn't notice. So his name is Hank Monkhorst, and he designed, if you don't like this file, you should kick them then. I was so, when I was hired to University of Florida as a postdoc in like 2007, and I thought all big names who you see in textbook, they are like in the past. And suddenly, like I walked through the like corridor with name tags on the offices. I say, oh, I saw this name when I was running the code. Okay, so 111 means 1 key point in each direction. 000 means velocity of the average wave is 0 in each direction. If we would want it to move, we would change the last number. If you want several waves coexisting and moving in different direction, we will make this file longer. Now, I think everyone can copy it, right? Now let's copy another template. So there is a subdirectory in car, and it has several templates. So some of them you see this bisrelip. So Adam, you recognize it, right? It's typical functional for Gaussian, right? So there is a template to run bisrelip, CHEM676, and there are many different things. Right now, we need only the simplest one for geometry optimization. So I'm taking the in-car geometry optimization, and I rename it in the current directory as in-car, because the names are standardized. If I name it different way, VASP will not recognize it. So let me copy paste this in the command in the chat. Paste. enter. Now let's look inside more in car. So I am going to modify it so that I do not waste your and my time right away. So the number of NSW, line number 2, 3, 4, 5, 6, 7, is like a breaker telling like if geometry is not optimized in 150 steps, it will stop anyway. I want to stop in one step, so it will be no geometry optimization. It will be just self-consistent field. As we go through the semester, we will learn how to modify these parameters, but right now let's take it just as a template. So I suggest you change NSW to 0 with other number. You will immediately get optimized geometry, but it will take like, instead of 30 seconds, it will run for 15 minutes, which we may not have right now. Escape WQ. Do you really want to write to it? Yes. Okay, ls minus OT. I do have 4 files: in-car, kpoints, postcar, podcar. So we are going to run WASP software on this Photon server with understanding that Photon server is our good friend, but it is not very young and not very strong. So it can be used only for little exercises. As soon as we get to realistic molecules, we need to do things on the remote high-performance computer, which I hope to show today after we complete the minimal task. So the executable of the WASP is located in the binary WASP-photon. So let me copy it. Copy. Chat. Paste. Enter. So if I know predominantly that the job will be short, I can hit enter. If I'm not sure that the job will be short, I can direct the output into like my output and then put ampersand, because otherwise it will block the command line. Just giving it so that you do educated selection of the command that you use. Paste. But right now I know that it will be a quick job, so I'm not doing this measure. So I'm just bravely hit enter. And what I see, it shows number of iterations. So those are self-consistent iterations, very similar to what we had in the Hartree-Fock when we did this quiz, when I think Adam was showing it again, a flow chart where it iteratively repeats. And at each iteration, it improves orbitals, improves total energy, which is like shown here. So it starts with positive and then it gets negative, 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 negative. And then at the last steps, they do not differ substantially. They're basically the same. The difference in the fourth digit, and then it tells, okay, done. So I'm going to make a tour and make sure that everyone arrives to the same image or similar image of the completed calculation. Okay.
I think I've made this change in the file.
No, let me. Okay.
No, I didn't.
VI. X. Okay. No, 0. I 0. You need to type I for insert.
Oh, okay.
I.
Oh, okay.
0. Now escape column WQ. Enter.
Oh, okay.
And now tilde.
Uh,
Do you have key points?
I think I have this here.
Okay, it looks healthy. Do whatever. Okay. Do you have key points? More erase, more space upper K.
Uppercase key points.
Okay, enter. Okay, now do tilde slash bin slash wasp lowercase VASP dash, not slash but dash photon pH. Enter. Okay, it goes constructively. Okay, good. Okay, yes. Yeah, that's good. Okay.
It's not opening here.
HOT. Looks correct. Let's just remove and redo the Podcar. I don't know what was wrong, but it goes. My pleasure. Okay,
But it's still running.
because you didn't change 150 to 0. But you, with the luckiest of the class, you will have optimized geometry. Well, we'll finish the story. It will be done.
Yes, the same problem. So it's still running.
Okay. Well, if right now let it run, or maybe you can open another directory and rerun a corrected single point job in different directory. But you can wait until it is done and then do things with optimized geometry. Do not worry. Okay, good. Thanks. Okay, and let's check online. Hanman, would you please share screen? Excellent, thank you. You can stop sharing. Sarah, would you like to share a screen? just scroll that I see. Did it arrive to the?
So this is my output.
Just hit enter several times because Zoom panel is blocking the. Okay, yeah, I see it. Very good. Yeah, thank you. You can stop sharing. Okay, we are progressing really well. So the output of the Gaussian is named .log. If you wait, what? Share screen. Okay. LS minus OT, and we finished with the job was starting when we had only so many files, right? At 6.16, and then after the job started, it created another dozen of files. So you see, Gaussian uses one input and creates two outputs, right? .log and .check, and WASP creates several files. Some of them are very analogous to what is in Gaussian. So the Podcar here is an analog of the .log file, and with some additional specifics and details, it contains the same information or very similar. The Wavecar, which is biggest or the second biggest, is very similar to .check file. So it contains orbitals, and it is has enough information so that if you want to continue job where we stopped, it can read information from there and continue. Today, it is not as important when we have powerful computers, but if your model is on the border of cutting edge of the size and productivity, sometimes one can run half of a job, store this analog of check file Wavecar, and then next day or in the next job restart it, because some big clusters do not allow jobs longer than 24 hours, right? And for us, the Wavecar is important because we will pull orbitals from there and plot them. The CHG and charge car are charge densities that Payman was plotting and discussing for us, right? So, but now we need to look into the, just a second, and log pot is the effective core potential on the language of Gaussian, but we do need the outcar. So more outcar. There is a lot of information that basically one can skip. And what is interesting, there are iterations, and after each iteration there is a list of orbitals. So a list of orbitals look the same way as we saw it after the processing of Gaussian.log file for making density of states. So same as Gaussian, at the end there is a in Gaussian there is a normal termination message, right? In WASP, if it is normal termination, it gives report on used time. So this job was finished in 6 seconds, which is quite impressive. So we need to identify only, by now, we need to identify only the list of orbitals, because we know what they are and which information we can get from them. So as you see, it has the number, energy in electron volt, and occupation. So those that has index 2 have 2 electrons. Those that have index 0 have no electrons. So they are analogs or like literal copies of the occupied and virtual in Gaussian, right? and we do need to use them to build the density of states. So there are scripts that extract this information, but I think it is a little more educational just to copy paste this portion. So I'm just copy this. So I scroll through, identify this part, and copy this list of orbitals. Then I stop and create new file, vi states. In the file states, I type I, and then paste this information, and then do an escape WQ. So more states, it gives this list of orbitals. So I recommend we just manually extract these files. If you, and we do not need more for right now, but if you're really annoyed by necessity to scroll through big file, one can just see that before this list of orbitals, there is a keyword Fermi, and one can look for keyword Fermi in the file Podcar and print 30 or whatever 20 lines after this keyword and direct it into a new file. But again, I recommend just manually copy paste the list of orbitals so that we touch it by hands. So I'm inviting everyone to just create this file and copy paste the list of orbitals, and I will make a tour and make sure that we all are on the same page. Podcar, yes. Okay. We may want to erase last line, which looks like empty line. You know how Gaussian sensitive to this. DD.
What's DD?
Delete the line. Escape WQ.
That's so cool.
Okay.
This is the outcome file. I can't find that information.
Let's copyright.
Okay. Oh, okay. Sorry about that.
That's okay. Okay,
Yeah,
please keep
yeah.
going. And use the same name, states with uppercase. Okay. VI. Escape WQ. It's better to give the name right away. Well, just Q, maybe Q exclamation. Column, escape column, Q exclamation. Q exclamation. Yes. States, uppercase states, enter. I, paste. Not enough. Escape, let's do escape. Escape column Q exclamation. Space.
Oh.
So you don't need this. Start from one. No, over only data, only numerical data. Yep. Arrow up. Yeah. I. No, it should be. Let's do escape Q exclamation. Let's just scroll. It's still here. No, not too far. It's very close to the end. Maybe like a couple of, yeah. Do not do copy, or just copy. Okay. If you do arrow up, I and paste. Escape WQ. And let's do VI once again. Do VI states once again. Type DD, D, and now escape colon X WQ. More states. More. Okay, excellent. Thank you. Okay. Oh, I think, okay, yeah. I space, just so that, no. Let's go to the first line. Let's make them all homogeneous. Yeah, excellent, thank you. Still running. Okay, let's just interrupt it. Just by Control C. Okay. Tail minus N 500. Podcar. So it is the latest set of orbitals that you've got, right? Copy, paste, and put it in those file states. Let's just interrupt it. We'll see. Minus N, let's see, 500. Car. A little bigger size. Can you please copy to the clipboard? Okay, now paste. Okay, great. Escape DD, just letter D 2 times. D. Huh? Yes, escape column WQ, column WQ. Oh. We need to erase it. Can you paste? Just move it over, yes, and erase the last line. escape DD. Well, this way it works as well. Now escape column WQ. Escape column WQ. More space states. Excellent, thank you. Okay, let's check online. Hanman, would you like to share screen? Let me request control. Thank you. So the VI states right now there is an empty line at the bottom, which may confuse the subsequent programs. So I delete it by either escape DD, or some of you do it by like backspace and then column WQ. Now more states. You see there is no empty line. Make sense? You can type WC for word count states. You'll see 21 line. So it should be consistent. And as a just next step, grep Fermi outcar. We will need this information. Grep number of electrons outcar. Grep number of ions outcar. Outcar. So you can stop sharing. You'll use this information a little later. Sarah, would you like to share a screen?
Yes, here it is.
Okay, thank you.
So let me do more.
Perfect, thank you.
Thank you.
You can move make it homogeneous by moving this one a little tabulated, but it may work without it. Okay, you can stop sharing.
Okay.
Thank you. So we are doing good, but it maybe we will do only minimal task today because time is running late. So now, same as with Gaussian, we want to convert this list into a graphical file. So we will assign a Gaussian profile to each energy of orbital, right? But there is a little challenge that one may experience if one wants to compare density of states of very heterogeneous systems. For example, some of you are thinking about quantum dots, right? And quantum, like piece of semiconductor of different size. And if one wants to compare like quantum dot of 10 atoms and 1,000 atoms, since number of orbitals is proportional to number of atoms, the one with 1,000 atoms will have, when we merge together, I think Hanman was answering this question, when several lines, several Gaussian profiles are added together with big widths, it will pull it up. And the one with 10 atoms will be very small. It will be indistinguishable by human eye. And one may want to normalize density of states, like divide everything by number of electrons or number of ions, stuff like that. So for future possible comparison of heterogeneous systems, we can make some measures and normalize density of states. So a couple of steps that I will show will implement this thing. So if you want to perform this normalization, we may want to learn how many ions were in this model. We know it was 9, right? For most of us. Some of us tried a model with like 18 or 19 atoms, but we just need to know it. Now, do you know how many electrons is in your model? It's easier. If there are 16 orbitals with 2 in each, it will be 32. But sometimes I'm stressed, I'm busy, I'm not focused. It's better to pull this information directly. Alternatively, one can count, like each hydrogen has 1 electron and so forth. But if one takes measures about the heavy atoms and accounts only valent electrons, it's better to ask WASP, like, hey buddy, how many electrons did you consider in this specific job. And this question is can be formulated this in the following way. Grab number of electrons in the out car. So it tells number of electrons equals 32.000. Chemical accuracy of concentration. Now, how many ions? Grab number of ions in out car. Number of ions equals 9. When you were doing, or we all together were doing density of states in Gaussian, you've noticed that we kind of speed up and we considered only two models, one titanium hydroxide and another complex, like titanium with six waters. Ideally, we should have a couple of homeworks with more models, but you've noticed that valence and conduction band in these two different models appear at dramatically different absolute energies. Once it was like -13 and 0, and another it was like -30 and -20, right? So what if you want to compare these models to put this density of states on the same image? Would it be reasonable to shift them in such a way that they have like centered in the midway between HOMO and LUMO or something like that, right? So we need to make some measures to compare several density of states. In this, for this purpose, we may want to bring in a concept of so-called Fermi energy. Who has heard about this concept? Okay, just it's not an exam. Just share what you've heard or what you think about Fermi energy.
From what I can remember, it has to do with how, or it's connected with electron degeneracy or pressure. So it's like the structure of an atom will, or like it will. I can't remember.
Okay, that's fine. So basically, Fermi energy is a midway between HOMO and LUMO for us simple guys. Some people define it a little bit differently, and it makes a lot of sense if one has many K points, if one has metals, and there are fractional occupations of orbitals, then all orbitals with, when there is no gap, all orbitals below Fermi energy are occupied more than half, probability more than 50%. All orbitals above Fermi energy have a probability of occupation less than 50%, if it is like thermalized fractional occupations. But for us, it's like a midway between HOMO and LUMO, right? So we can ask WASP once again, like, what was your Fermi energy for this model? So grab Fermi out car. It was okay. For me, it was -6.9. And sometimes by algorithms, it is closer to HOMO than to the LUMO. It's not midway, but almost the HOMO. But we are not going to argue. It is what it is. But these pieces of information will be used towards making an educated, smart dose that can be compared with systems of similar stoichiometry, but much bigger number of atoms or much smaller number of atoms. And the last thing that I want to make sure, how many lines are in my states file? You may think that I'm crazy and I do not know arithmetic, how to count from 1 to 21. But what if it will be 2032 atoms, orbitals? I better count them by WC for word count. It's not different abbreviation. Word count states. And it tells, okay, 21 lines. So the information from this 4 little, how to say, measurements, experiments will be used towards creating density of states. I have a message that not, well, I need two introductions that if you go to everyone. Haley was taking physical chemistry course where we all were learning MATLAB software. And she was teaching the whole class how to do little scripts. starting with a simple dialogue where the script is asking like I am a MATLAB script. What is your name? Then you type in the name and then hello, and then it retypes the name, right? So a dialogue. It's a very standard style how people learn programming. I went through the same thing in my time, and when the script was created, it is not far from this psychology. So instead of elegant programming where things are being read from input file, the script that we are going to run will establish a little dialogue that is similar to what Heavy was doing in other class. So it will ask us, so the code will ask us, how many lines in your code, how many in your states file, how many electrons, how many ions, what is the Fermi energy? And we need either copy paste or type the answer. It's not a big deal, but it's not a commercial, it's handwritten code, and try to do it without errors. If you do backspace or you hit error by enter by the error, it may screw up the running of the code and you better restart. So it's not a big deal, just prepare. I'm giving heads up. So, and it will not use more information that is shown on this panel. So the script is in binary address DOS norm. Just in case, if you're interested to look inside the script, there is a source code address DOS norm.f. It's like maybe 20 lines Fortran code. Let me copy paste this one into the command line. Not command line, in the chat. Paste. And now I just go forward with it. Enter. So number of states I'm certain 21. Minimal energy and maximal energy and energy Fermi. Okay, so it's the same information as we used for Gaussian. So I see that the HOMO is -7, LUMO is -3, and probably I want to show density of states in the interval from -8 to -2. So I will type here starting at -8, ending at -2. Then for the Fermi energy, I copy paste this one. And for alpha plus beta, it's correction for the fact that there are alpha and beta electrons. I just copy paste this one. So 4 numbers, enter. Enter width of each line. And it, for example, 0.01 electron volt. I can be a little bit more radical and put 0.05, a little smaller. Magnitude 1. Number of atoms in the simulation cell, 9. Number of electrons in the simulation cell, 32. Gap of bulk phase of the same material. It will not change anything, but we know that for titanium dioxide, it's like 3.2. And then it tells all is okay. I'm confident you can do it for sure, but just in case, I'll copy this dialogue so that you feel secure and confident. Okay. So after doing this dialog, I'm checking ls-ot to see if there are any new files. And it does show a file named dos.fermi. So this is the same file as we had, like dos.log, dos-alpha.log, dos-beta.log. So if we look inside, it will show columns that correspond to energy and columns that correspond to the value of density of states. There is a script that converts this file into the graphical file. Bin GNU prog _ DOS. So who was presenting on converting on this subject? Who was presenting on the script? I think there were several presenters, right? One of them was Anand, right? You were showing how to plot density of states with GNU plot, correct? And another, I think, was Hanman, who is online right now. So this script will take this DOS Fermi file using columns 3 and 5 and 3 and 4 and plot the result into the file named dos.ps. So the most practical way is just to type GNU plot and then this script. So let me copy paste this one into the chat line. Paste. And after running this script, there should be, there is a new file dos.ps. So PS is very ancient format. We want to convert it PS to PDF. Write dos.ps. And after this command, we have a PostScript file. Not PostScript, PDF. So I can copy paste it either by SCP, or there is a way we will suffer SCP commands again and again, but let me just find the directory where we're working on the left panel. So chem year 22. I'm looking for my subdirectory. It's lab number 9. And here is the dos.ps. So I'm clicking on it here. And it brings up the file in the PDF to this computer. So the occupied are highlighted like this field, and unoccupied are empty. And if you compare it with numerical data, occupied that has 2 electrons per orbital are around -7 electron volts. Those that are empty are about -3.8. Okay, so let me make a tour. Yeah, probably this dialogue is most important. Let me make a tour and make sure that everyone is on the same page. Oh, great, thank you. Okay. No, just convert it to PDF. PS to PDF space DOS. Enter. PS to PDF R. WR for me right.
Right.
And okay. Now let's. Okay, this is already.
Oh, is
Okay.
is that disconnected?
Okay, then we need to extend just.
Oh, I think it's connected.
Is it?
So, oh. Okay, I will copy it to my.
Yeah. Okay, yeah, thank you. Oh, blue plot.
New plot.
Uh-huh. G and U plot space tilde tilde slash bin slash gnu prog underscore dos. Enter. PS to pdfwr space dos.ps. Enter. And if this one is, yeah, if this one it was not okay, and this off. New, I think you are new. Super. Okay. Rizvi, what is going on? It happens, don't worry. Okay, more states. States, okay. Let's do grep firma. That's fine. That's fine.
I'm putting these.
Wait. 21. Okay, let's do over. Oh, let's type 8.
Minus 6.
Yeah, excellent. Thank you. And did you get it? Mhm. Oh, it's okay. Which one? Which director? Oh, you're doing in my directory. It's not right. You need to do in your directory. So do not write in my directory. Okay. Uh, 21. Okay. And you just need to go. The last one.
Yeah, he's the last one.
Yes. 35. 18. Number of electrons.
51.
Um, Perfect, thank you. Hanan, would you please share screen? Excellent, thank you. You can stop sharing. Sarah, would you please share screen?
Yes.
Thank you.
But I didn't upload the. I couldn't display the .ps file.
Okay, let me request control.
Yes, sure.
And just download this dos.pdf to local computer and see how it looks like.
Okay, I will do that.
Okay,
Thank
yeah,
you.
thank you. So I think it was enough for today. I will try to send to like, if anyone wants to meet on the break, send me email and I will coordinate. Also, to make your week, your break a little bit more pleasant, I will design homework. Maybe not very hard, but something that we just solidify our skill for density of states. And those who will not elect, maybe no one will elect to meet on the break, we'll see in Monday, Tuesday, Wednesday in 2 weeks for getting background of density of states and continuing our journey into the VASP software. So on one hand, we need to do at least the same things as we did with Gaussian, like orbitals, total density images. And for this, you all will need to download the VMD software. It is free. It will ask for your email, but it will not charge anything. And on the other hand, we need to be able to do the same things on the outside cluster, which would take maybe another half an hour, but we do not have it right now. Well, we'll do it either during the break or after the break. Yeah, many thanks for investing your time into this course. I'm really happy that there are attendees. Wishing you high grades on the rest of your midterms before the break and pleasant break. Looking forward for your emails, and I plan to send you some emails as well. Okay, meeting is done. Everyone is welcome to disconnect and depart. If you are on the photon cluster and you are done with your exercises, it will be a good thing to type exit before finishing, so that system administrator will appreciate it.
Okay, thank you.